We'll draw our circumcircle and the acute triangle ABC inside. Then I'll draw these altitudes from C and B. These points are P and Q, and I'll extend PQ to the sides of the circumcircle. So this is X and Y. And we have these lengths, 10, 25, and 15 on the purple segment. Right away we can do power of a point. At P, we have XP times PY is AP times PB. Substituting for XP and PY, we have 10 and 40, so this product is 400. Power of a point at Q, the product of XQ and QY, that's going to be the same as AQ and QC. 35 times 15 is 525. With a lot of advanced AIME geometry problems, we often make progress by looking for cyclic quadrilaterals. Right angles help us do that. If you look at right triangle AQB, we see that AB is the hypotenuse opposite this right angle at Q, so it can be a diameter of the circumcircle of that right triangle. We also have right triangle APC here on the right. AC is also a hypotenuse, so we can also use it as a diameter of the circumcircle of that triangle. And finally at the bottom, we have right triangle BPC, giving us another diameter BC. To find the cyclic quads, my AIME hack is to draw simpler diagrams with only the information that we need. Let's start with our diameter AB here on the left. I'll redraw my triangle ABC with its two altitudes from C to P and B to Q. Let's draw our third altitude from C, and we'll call this point R. The altitudes all coincide, so it's going to pass through this intersecting point. Well, let's draw our circle that has AB as a diameter, and we have right angles here at Q and R. So Q and R are going to be on this circle, here and here. And before we go forward with this, let's repeat this with our three other diameters. Redrawing the triangle really quick, and the altitudes. BC is our diameter here. And with right angles at P and Q are also going to be on our circumcircle. And finally, diameter AC. And P and R are both on this circumcircle because of their right angles. Let's return to our first circumcircle. I'll complete this cyclic quad by drawing in segment QR. If you look at this arc from B to R, it is cut off by these two inscribed angles at A and Q, so they're congruent. Let's extend these segments from A and B to complete our triangle ABC. Here's C. Note that angle BQR and the angle next to it, RQC, these two add up to 90 degrees because it's opposite this other 90-degree angle, AQB. Now angle BAR and ABR also add up to 90 degrees. This is because they are both the acute angles of right triangle ABR. Since BAR is the same as BQR in both of these sums, we have that angle RQC is the same as ABR. And in the context of our whole triangle, that's the same as angle ABC. Now we'll repeat this 2 more times with our other circles. I'll join PQ, completing our cyclic quad, and extend these segments to complete triangle ABC. Looking here at arc PB, these angles from Q and C cut off this arc, so PQB is the same as PCB, and PQB and PQA right next to it sum to 90 degrees. And then looking at right triangle PBC at the bottom, we have angle PCB and PBC are the two acute angles of this right triangle, so they also sum to 90 degrees. These two are the same, so angle PQA is the same as angle PBC. Let's redraw triangle ABC once more. So we have this angle over here, ABC, and if I draw in segment QR, that's going to be congruent to angle RQC. So what we have, because of the shared angle here at C, triangle ABC is similar to RQC. Let's go on to our next cyclic quad. As above, we'll look for our similar triangles by simplifying our diagram again. I'll draw PQ here. We have PQA over here is congruent to PBC down below, and they have this shared angle at A. So we have that triangle ABC is also similar to triangle AQP. And now with our third cyclic quad, connecting segment PR and extending A and C to meet here at B, completing our original triangle. Here's our arc, RC, and it's cut off by these inscribed angles here at P and A, which gives us RPC and RAC. We can use RAC because it's an acute angle of that triangle. We'll add it to RCA to get 90 degrees. And with angle RPC, we can add it to its adjacent angle RPB to also get 90 degrees because they're on this side of the right angle and the other side of P. These two angles are the same, so we have angle RCA is the same as angle RPB. We will redraw our triangle to find our similar triangles. Here's PR, here's RCA, and RPB, and this shared angle at B again. So we have triangle ABC is also similar to triangle RBP. So let's summarize all of our similar triangles here. The big triangle ABC is similar to the one on top, AQP, the one on the left, RBP, and the one on the right, RQC. So all of these angles in these four triangles, the big one and the three on the outside, are going to be congruent. Let's go ahead and call these angles X, Y, and Z, and being careful to assign them to the correct corresponding angles, we'll do the same thing with two other triangles. From the problem statement, we already have that this length is 25. And from our earlier power of a point, we have these products. Since we have AP and PB in our first power of a point equation, let's compare similar triangles APQ and the triangle with PB, RPB. We'll use these two sides of the triangle on the left, AP and PQ, and the corresponding sides, PR and PB, of the triangle on the right. And we'll solve for PR. From power of a point, we have 400 in the numerator and 25 for PQ. This gives us 16 over here. We'll do the same thing to get this third side length QR. Triangle APQ is similar to triangle RCQ. This time the two sides will be AQ and PQ, and the corresponding sides will be RQ and CQ. And we'll solve for RQ. AQ and CQ multiply to 525, so this distance is 21 over here. Now we're going to use the lengths of triangle PQR and see if we can translate them into the lengths on the outside of our triangle. We'll do that first by using the law of cosines to translate these lengths into an angle. Then we'll use the half angle formula, and finally we'll use the law of sines to get these outer lengths again. First, let's take a look at this angle here, PRQ. This is 180 minus 2x from these other x's on either side. So we'll find the cosine of this angle. The cosine of 180 minus 2x is the negative cosine of just 2x. And from law of cosines on triangle PQR, this reduces to 3 over 28. Now we'll use the half angle formula for sine. Cosine of 2x is the negative of 3 over 28, so we'll add 3 over 28 in the numerator. Simplifying, we get root 31 over 56. And we'll repeat this with angle RPQ, that's over here, which is 180 minus 2y. So the cosine of angle RPQ is the negative cosine of 2y. And then we'll use law of cosines again, using the side lengths of that inner triangle. This is 11 over 20. So we'll add 11 over 20, and this sine is 31 over 40. Then we'll do this third angle up here, PQR. And law of cosines again, this is 27 over 35, and sine of z, plugging in, this simplifies to root 31 over 35. Let's summarize. In the problem, we're asked to find the product of AB and AC. We'll replace AB with AP plus PC and AC with AQ plus QC. And then we'll find all of these lengths. We'll do that using law of sines. In triangle APQ, on top, we have AP over sine of z is PQ over sine of x. And we'll solve for AP. This is 25. Sine of z over sine of x, the 31s are going to cancel. We'll have 56 over 35 here. And this will simplify to 10 root 10. And we'll repeat this with the triangle on the left, triangle PRB. We'll take PR over the sine of the opposite angle, z, and we want PB. That'll be over sine of x. And we'll solve for PB. This is 16, and we just have the reciprocal of the square root above here. This gives us 4 root 10. Let's find AQ by using triangle APQ again, and solve for AQ. Here we have 25 again. The 31s are going to cancel again, so inside the square root, we'll have 56 over 40. And all this simplifies to 5 root 35. And now we'll use triangle QRC. We want to find QC. This is over sine of x. We know QR. That'll be over sine of y. Then we'll solve for QC. QR was 21, and this fraction is the reciprocal of the previous calculation, so 40 over 56, and this simplifies to 3 root 35. So AB times AC is the product of these two sums, and we'll plug all this in. Multiplying and simplifying, we get 560 times the square root of 14. The problem asks for m plus n, and our answer is 574. If you'd like me to solve any other math contest problems, please leave them in the comments.